So, dear students, welcome to the new lecture of Basic Electrical Engineering. In this particular lecture, we will continue with the concept of practical transformer on load. And in this particular lecture, we will understand how to draw the phasor diagram of a practical transformer for an inductive load. That means for the lagging power factor, similarly for the resistive load, and then for the capacitive load. So now before that, we need to understand the various important parameters that we will encounter in this particular lecture. So before that, let us see the equivalent circuit of the practical transformer on load. In our previous lecture, we have already understood about the equivalent circuit of a practical transformer under load condition. Now, uh, so all these parameters which are mentioned here will be considered while drawing the phasor diagram of the practical transformer for various types of loads. So here in this V1 is the RMS value of the input voltage V1, right? Then I1 is the RMS value of the full load primary current. Then similarly, I note is basically the RMS value of the no load primary current. Then we have I2 dash. So this is equal, this is the RMS value of the full, uh, or you can say the primary counter current. In our previous lecture, we have already understood the significance of this particular current. It is generally equal to I2 by A, where A is the transformation ratio. In some books, you will also find I2 dash as equal to KI2. So here K is also the turn ratio or voltage ratio basically, or transformation ratio, right? Now let us come to this E1. So E1 is the RMS value of the induced EMF in the primary winding, and R1 and RX1 basically are the winding resistance and reactance of the primary winding. Now, similarly, R naught and X naught are the uh, core parameters under no load condition. So we have already understood the significance of R naught and I naught. So this is IC, so we can take it as IW because we are already taking this as IW as a notation. This is IM, so IW is the RMS value of real component of I naught, and similarly IM is the RMS value of the magnetizing component of I naught. So these are the parameters which are associated with the primary winding. So all these parameters are associated with the primary winding. This is the primary side of the transformer and this is the secondary side of the transformer. So similarly we have E2. So E2 is the induced EMF, or you can say RMS induced EMF in the secondary winding. V2 is the RMS terminal voltage. ZL is the load impedance, and these two are basically the resistance and reactance of the secondary winding, right? So these are resistance and this is the reactance of secondary winding. So these are the parameters basically which are associated with the transformers equivalent circuit. So let us consider this to be a node A, or let us say it is node A. For example, we'll take it as node 1, right? So at node 1, if you apply KCL, so at node 1, KCL equation is I1 is equal to I naught plus I2 dash, right? Now if you apply KVL in this particular loop, so let us assume that there is certain voltage V1 dash at this junction. So let V1 dash is the junction voltage of node 1. So if you apply KCL here in this particular loop, so it will be V1 minus I1 R1 plus X1 minus V1 dash is equal to 0. So from here we have uh, V1 dash is equal to V1 minus I1 R1 plus X1, right? So this is, let us say, some equation number, for example, this is equation number 1, and uh, this is, for example, equation number 2, right? So we will need all these equations while drawing the phasor diagram. Similarly, if we apply KVL in this particular loop, so this is, so the equation would be E2 minus I2, and this is R2 plus X2. So this is minus V2 is equal to 0, right? So you can say that E2 is equal to V2 plus I2 R2 plus X2. So this is, for example, our equation number, uh, for example, this is equation number 3. So let us mark it as equation number 3. So now we have three equations, I1, I2, sorry, equation 1, equation 2, and equation 3. So all these parameters are some important parameters, and we will require all these parameters while drawing the phasor diagram. So let us come to the phasor diagram. Now, first of all, we will consider and we will assume that our transformer is connected to an inductive load. So that means this ZL in this case is inductive in nature. Okay, so this is uh, inductive. So when we say inductive, we do not mean to say that it is a pure inductor, but it is a combination of the resistance and inductor, right? So it could be your RL load, right? So we will understand here about the phasor diagram if the transformer is connected to the RL load, right? Now we know that in an RL load, the current lags the voltage by some angle phi, right? So this is what we need to understand. Okay, in a pure inductor the current lags the voltage by 90-degree, but in some RL load, which is not a pure inductive load or pure resistive load, so in an inductive load the current lags the voltage by phi radians, right? So now let us start with the phasor diagram. So first of all, because we know that our transformer windings are mutually linked with the mutual flux. So mutual flux will be the reference phasor, and that is why we will draw this reference phasor first of all. So let us draw side by side on this side also. So first of all, we have phi m, right? After that, from the EMF equations, we know that because phi is given by phi m sine theta, and we know that the EMF equations are given by EM1 sine theta minus 90-degree. Similarly, E2 is given by EM2 sine theta minus 90-degree. So this is what we have got from the EMF equation of the transformer. So we'll write here from the EMF equation concept, right? So from this concept, we have these mathematical expressions. So from here, we understand that the EMF equations, EMF induced EMF basically will lag the main flux by 90 degrees. So let us draw. So secondly, the firstly we will draw the reference phasor, that is mutual flux phi m, then E1 and E2. So let us draw here side by side. So first of all, E1 and then E2. Both are in same phase, right? Now, the next thing that we will draw is the voltage V2, right? Voltage V2 is the terminal voltage of the transformer. So let us draw voltage V2. So voltage V2 is this one, right? Okay. Now, because our load is inductive in nature, so the current that flows in the secondary winding, that is I2. Okay. So because ZL is inductive, hence I2 lags V2 by phi 2, where phi 2 is the secondary phase difference angle, right? So let us draw the current I2. So I2 will be drawn here like this, and I2 is lagging V2 by angle phi 2, as you can see here in this particular diagram, right? So we will write this also, and we will draw in our own figure. So let us draw I2. So I2 is, let us say, this one, and these two have a phase difference which is phi 2. Now, the next thing that we will do is we will consider the uh, uh, now, if we see the secondary of the transformer, let us draw the secondary of the transformer here. So in this we have a resistance R2, we have an inductor X2, and then we have a load impedance which is ZL, right? And then we have, this is the secondary side, right? Secondary winding, fine. So this is some current I2 flowing here. Here we have the induced EMF E2. Here we have the terminal voltage V2, right? Now, when this current I2 flows through this resistance R2, there will be some voltage drop here which is I2 R2, right? Similarly, there will be some voltage drop here, which is I2 X2, right? Now, this I2 R2 is the voltage drop. So the phase difference between this I2 and I2 R2 will be 0 degrees. Okay. So this is I2 and this is, let us say, I2 R2. So both will be in same phase. R2. Similarly, here in this case, in case of X2, uh, uh, the current will lag the voltage by, or voltage drop by 90 degree. So that means we have I2 X2, and current is, let us say, lagging. I2 is lagging, right, by 90 degree. So that means from here, from V2, we will draw a parallel phasor which represents I2 X2, because I2 R2, not I2 X2, it is I2 R2. Okay, so this I2 R2, because is in phase with I2, so we will draw this in parallel to I2. As you can see, these two lines are parallel. So let us draw a parallel line with I2. So this is our I2 R2. So as you can see, in these two parallel lines, there is no phase angle. Okay, parallel lines do not have any angle. Basically, the angle between parallel lines is zero, right? Then then we will draw, because this is the voltage phasor, this is the voltage phasor from here like this. So we will draw this voltage phasor also, this I2 X2, because I2 X2 will lead this current I2 by 90 degree. So we will draw this at 90 degree from angle. So if you extend this here, so this phasor is 90 degree from, though this phasor I2 X2 is leading the current phasor I2 by 90 degree. So let us draw here. So take angle 90 degree and draw it like this. Okay. So this is our I2 x2. And you can see here that E2, so this is E2, so E2 is equal to V2 plus I2R2 plus I2X2, right? So, or we can write it as V2 plus I2 R2 plus X2, right? So, you can apply KVL in this particular mesh, secondary mesh. So you will find the same equation, E2 minus I2R2 minus I2X2 minus V2 is equal to 0. Okay, so if you rearrange this equation, okay, we have already done this on the first slide. You can refer the first slide for this, right? So if you rearrange this equation, you will get this particular equation. So it is being justified by the vectors also. So E2 is equal to V2 plus I2R2 plus I2X2, and this is like this. Okay, so now let us proceed further. Okay, now this is the phasor diagram of the secondary side of the transformer. Okay, now let us draw the primary side also. We'll draw the primary side here itself. So the primary side is something like this. We have a resistance R1, we have an inductive reactance X1. Then we have the core parameters, right? And we have like this, and we have the primary winding. Okay, so let us write the parameters here also. So here we have I2 dash, the voltage between this point uh, is E1, these two terminals. This is R naught, this is X naught. The current here is I W, the current here is I mu or Im. This is R1 and this is X1, and we have the input voltage which is V1, right? So if you apply KVL in this particular mesh, so let us say this is junction 1, and at this junction the voltage is V1 dash, right? So we will get V1 is equal to not equal to V1 minus I1 R1 minus I1 X1 minus V1 dash is equal to 0. So from here we have V1 is equal to, or V1 dash is equal to V1 minus I1 R1 plus X1, right? So that means the current which flows here, this current I2 dash basically, now this current is eventually responsible for the self induction or self induced EMF E1, right? So that means the cause of this EMF E1 is V1 dash. Okay, so we will write it here. Cause of E1 dash is not E1 dash, sorry, cause of E1 is V1 dash, right? So let us erase all these from here. So hence, as per Lange's law, E1 opposes V1 dash, right? So that means we will draw a new phasor. Instead of V1, we will draw a new phasor V1 dash on the upper side opposing E1. So let us draw this one. Okay, now this green line basically indicates this phasor, some of these two phasors, I2R2 and I2X2. So this is not significant. It is simply drawn here just to make it bit attractive. Sorry. So now Now, first of all, we will see this I2 dash basically. What is this I2 dash? This I2 dash is basically a counter primary current. Now, what happens in our previous lecture, if you have watched that lecture, but if not, then please watch that lecture. In our previous lecture, uh, in which we have discussed the practical transformer on no load and its equivalent circuit. So there we have understood this, that when the current starts flowing in the secondary winding of the transformer, it produces its own flux in the secondary winding, which counters the primary flux, main flux. So it tries to cancel out the main flux. Now what happens? Due to this, the main flux gets weakened, and this will lead to the reduction in the induced EMF in the primary winding, which is E1. So E1 reduces. So what happens because of this reduction in E1? V1 will increase. Okay, so V1 become greater than E1, right? So to counter this effect of the secondary flux, what happens? The primary voltage V1 tends to send more current to the primary winding, and this current is I2 dash. So this current counters the effect of the secondary flux in the primary winding, right? So that is why it is called as counter primary current basically. Okay, so this current is opposite to I2 because it is countering the effect of I2, and the effect of I2 is the secondary flux. So I2 dash counters the secondary flux by generating an additional flux in the primary winding, which assists the main flux in primary winding, right? And that is why we have drawn it in opposition to the I2, right? So now, because as I have already said that it is V1 which is being opposed by E1 as per Lentz's law. E1 is the induced EMF in the primary winding because of I2 dash. I2 dash is because of V1, right? V1 dash, sorry. So we will draw it like this. Then now let us come to, so we have E1 drawn, we have I2 dash taken up, we have V1 dash taken up. Now we have a no load current flowing here, right? There is some no load current flowing. So this is I naught. I naught. I naught is the no load current, right? And I naught is equal to IW plus I mu. So I naught is basically the resultant of these two currents, right? So now in this R naught, the voltage across R naught, so voltage across R naught and X naught is V1 dash, right? So current in R naught is IW. So IW and V1 dash are in phase. These two will be in phase. Why they are in phase? Because R naught is a resistance. So let us draw this one. So we have drawn IW phasor, which is in phase with V1 dash, right? Now I mu basically lags V1 dash by pi by 2 radians or 90 degree, right? So let us draw this one also. So I mu is lagging V1 by 90 degree, as you can see here, right? Now the resultant of these two is I naught. So let us draw the resultant, and the resultant is drawn here, which is I naught. You can see. So now I naught is obtained. Now we are left with primary current, main primary current or full load primary current I1, V1, I1 R1, I1 X1. So we will draw all these parameters one by one as phasor diagram, right? Now, now because from the equation number one, from equation one, so from equation one, we have I1 is the resultant of two currents, which is I0 and I2 dash. So these two currents, this one and this one, the resultant of these two currents is I1. So now we will draw the I1 phasor. So this is the I1 current, right? Now we have I1. Now when this current I1 flows through this resistance R1, so it will create some voltage drop across the R1, which is I1 R1. So I1 R1 and I1 are in phase. So these are in phase. So let us draw. How will we draw it is in phase? By drawing a voltage vector in parallel to I1. So as you can see, these two, this vector and this vector, these are in parallel. So there is no phase angle between these two, right? Now, when this current I1 flows through X1, so it will create certain voltage drop across S1, X1. So I1 X1 leads I1 by 90 degree. Why? Because X1 is an inductor, and we all know that in an inductor the voltage leads the current by 90 degree. So let us draw a perpendicular phasor which is I1 X1. So we will erase this one. Now, so I1 X1, if you see, if you draw it back, so it is almost perpendicular to this one. So I1 X1 is a voltage phasor. So in perpendicular to I1, because uh, the voltage leads the current in an inductor by 90 degree. Now, if we see this particular equation here, if we rearrange this equation, we have V1 is equal to V1 dash plus I1 R1 plus I1 X1, right? So this is the equation. Okay, so this particular equation is rearranged to give this one. So you can see that uh, V1 dash plus I1 R1 plus I1 X1 will be equal to V1. So now we have drawn the V1 phasor here, right? So uh, this is something to just give an attraction to this particular diagram. Now, in the primary side, we have two parameters, main parameters basically, V1 and I1. So the phase difference between these two is phi 1. Okay, so phi 1 is the primary phase difference angle, right? So this was about the uh, phasor diagram of the transformer when connected to an inductive load, right? So these are separate equations. So let me separate them by just highlighting. This is a separate equation of secondary winding, right? So now this was about the phasor diagram of a transformer for inductive load. Now let us see how to draw the phasor diagram of a transformer when connected to uh, a resistive load. Okay, so now see the phasor diagram in this case will again begin with the same concept. First of all, we will draw the reference phasor, which is the mutual flux. Then we will draw the induced EMF phasors E1 and E2 because they are lagging the main flux by 90 degrees. Then we will draw the secondary voltage, terminal voltage phasor V2. Now, because it is a resistive load, so in case of resistive load, uh, means if the secondary winding of the transformer is connected to a resistive load, right, RL. So the voltage here is V2 and the current here is I2. So these two parameters will be in same phase, and that is the phase difference between these two parameters will be zero, and it is shown here. Okay, so now the same thing we will apply. If this current I2 will flow through this R2, there will be certain voltage drop I2 R2. So I2 R2 and I2 will be in same phase. Why? Because R2 is a resistance, right? So these are in same phase, you can see, same phase, right? Now, when this current I2 flows through this X2, so there will be certain voltage drop I2 X2 across X2, and these two, so I2 X2 in this case will lead I2 by 90 degrees, right? So this is what's shown here. You can see. So I2 X2 is leading I2 by 90 degree, right? So this is for the secondary side. Now, first of all, we will draw the counter primary current phasor. So counter primary current phasor will always be in opposition to the this current I2 current, right? So it is totally opposite to the I2 current. Now we will draw V1 dash, because V1 dash on the primary side is the cause of E1, and E1 is opposing its cause as per Lange's law. This is been explained in the previous slide for the inductive load. Then, because in the core parameters, IW is flowing through R0, and the voltage across R0 is V1 dash. So these two are in same phase, right? I mu is flowing through X naught. X naught is an inductor. Voltage across inductor in this case is V1 dash. So in an inductor, the current lags the voltage by 90 degree, and you can see I mu is lagging the voltage V1 dash by 90 degree, right? So the resultant of IW and I mu is I naught, and the resultant of I naught and I 2 dash is I1, right? So now we will draw for the primary side I1 R1. When the primary current I1 R1 primary current I1 flows through R1, so I1 R1 will be the voltage drop across R1. So because it is a resistance, so the phase difference between I1 R1, you can show it here. So this is the secondary winding, this is the primary winding, right? So we have the core parameters also, right? So this is V1, I1, R1, X1, V1 dash, I2 dash, E1, right? This is no load current I naught, IW, I mu. This is X naught, this is R naught, right? So when this primary current is flowing through X1, so there will be certain voltage drop across this, which is uh, I1 X1, right? So I1 X1, because it will lead the primary current I1 by 90 degree, right? So let us draw this one. So you can see here, so if you draw it backward, so it is 90 degree leading the primary current, right? Now if you apply KVL in this particular mesh, V1 is equal to I1 R1 plus I1 X1 plus V1 dash, right? So this is the equation. So you can see V1 dash plus I1 R1 plus I1 X1 will give you V1, right? So now the phase difference angle between V1 and I1 is phi 1, right? So this is the phase difference angle you can see. So it is quite simple to draw the phasor diagram in this particular case, right? Now let us, now this is for the unity power factor basically. Now, uh, right, this is for the unity power factor. Now, why it is for unity power factor? Because ZL is resistance R. So, in resistance, the voltage and current are in same phase, right? They are in same phase. And because the load is connected towards the secondary side, so the same phase is being observed towards the secondary side only. However, towards the primary side we still have a phase difference phi 1, right? So this is the primary winding phase difference between V1 and I1. What is V1? RMS value of the primary voltage. What is I1? RMS value of the primary current. Now let us draw the phasor diagram of a transformer for the capacitive load. Again, first of all, we will draw the reference phasor phi m. Then we will draw the EMF E1 and E2, very simple. Then we will draw the voltage V2. Now, because this is a capacitive load, in case of capacitive load, the load current, because ZL is RC, right? Capacitive, right? So, in case of a capacitive load, the current leads the respective voltage by phi, right? So that is in this case I2, which is the full load secondary current leads V2, which is secondary terminal voltage, right? So now let us draw the phasor diagram of the current. So phasor of current is, let us say, this one. This is, let us say, I2. Okay. So we have the phase difference between these two as phi 2. Okay. So by phi 2, right? I2 leads V2 by phi 2. Okay. So now let us proceed further. Now what we will see, we will draw a counter primary current. So the counter primary current is the opposite to this I2. This current is I2 dash, right? So this is the counter primary current. Now because this E1 is because of V1 dash, so it is opposing V1 dash, so we will draw it here. So it is V1 dash, right? And uh, the now if you see the primary side of the transformer, so in the primary side of the transformer, the voltage across R node, the core parameter is V1 dash, and voltage across X node also it is V1 dash. So current through R node is IW, current through X node is I mu. So let us draw. So that means I mu will be in same phase. Sorry, IW is in same phase with V1 dash, right? And I mu is 90-degree lagging the V1 dash. So this is I mu. Okay. So the resultant of these two is resultant is I naught. Resultant of I mu and IW is I naught. Now, the resultant of I2 dash. So, if you see the primary side, I1 is basically I2 dash plus I naught. So, that means the resultant of I2 dash and I naught is, it is I1. So, let us draw I1. So, let us draw I1 uh, somewhere here it will be drawn. So let us draw it. So this is I1, right? So, right. So now from this V1 phasor, V1 dash phasor, we will draw one phasor which is, because when this current I1 flows through R1, there will be I1 R1 voltage drop, then I1 X1 we will draw. So I1 R1 will be in parallel to I1. So यहाँ से you can draw a parallel line. Then I1 X1 is 90 degree. So this would be uh, just a minute. So this would be, let us draw it a bit lengthy just to make a distinguish. So here it is, this is I1 R1, and from here you have I1 X1 90 degree, right? And then you have a phasor which is V1, because for the primary side V1 is equal to I1 R1. The same equation will be followed here also. So that means V1 will exist between I1 and V1 dash somewhere. So let us draw it a little bit broader. So this is, let us say, V1 dash. So from here you have I1 R1, right? And then you have this primary current also, which is I1 here, right? And from here you have I1 X1, right? So now V1 dash plus I1 R1 plus I1 X1 will give you V1, right? So let us draw V1 here. So this is V1, okay? So the phase angle between sorry, not this one. Uh, the phase angle between this V1 and I1 is phi 1, right? So we have simply, the expanded view is this one, right? So this is how we can draw the phasor diagram. We simply have to remember few points. First is draw the reference phasor, that is phi m, right? And second is draw E1, E2 by keeping them 90-degree lagging the phasor phi m, right? And then again the same few concepts are applied here. V2 will again is shown in this such a manner that, okay, V2 will always be behind E1 and E2. Why? Because in the secondary winding, if you apply KVL, right? So we have already studied this one in previous slide. So V2 is equal to basically E2 minus I1 R, I2 R2 and I2 X2. So V2 is E2 minus I2 R2 and I2 X2. So this is the resultant one, right? So that is why it is always shown behind E2, right? So this was the phasor representation of a practical transformer for under full load condition for different types of load, three types of load: inductive, resistive, and capacitive. Now, because this is a capacitive and current leads the voltage by phi, so we call this as leading power factor, right? So the phasor diagram here shown here is for the leading power factor. And this was all about today's lecture. Thank you so much.